Welcome back to the Learning Studio. You're watching our mathematics series in the section on data, algorithms, and computation, where we reveal the math-powering algorithms, AI, and the digital age. If you're new here, don't forget to follow us by clicking the link below. And remember, the full playlist is in the description, so you can explore the series step by step from the very beginning. Today, we'll dive into spectral theory, the study of eigenvalues and eigenvectors, and how they help us uncover hidden structures in data, networks, and even physical systems. Picture a massive social network, millions of users connected by billions of links. How do we identify communities, detect influence, or reduce this huge system into something understandable? Spectral theory provides the lens. By analyzing the eigenvalues of special matrices, we can reveal patterns that aren't obvious on the surface. It's like tuning into the hidden frequencies of a complex system. Core concepts, here are the essentials. Eigenvalues and eigenvectors. These describe the natural modes of a system, the directions where transformations act most simply. Graph Laplacians. By turning a network into a Laplacian matrix, spectral theory allows us to find clusters, communities, and connectivity patterns. This is the foundation of spectral clustering in data science. Dimensionality reduction. Techniques like principal component analysis, PCA, rely on eigenvalues to reduce high-dimensional datasets into their most meaningful components. Physical interpretation. In physics and engineering, eigenvalues describe vibrations, resonances, and stability, showing that spectral theory connects both the abstract and the practical. Why it matters in AI, computing, and technology. Spectral theory is at the heart of many modern applications. In machine learning, eigenvalue methods reduce dimensionality, making models faster and more efficient. In graph theory and network science, spectral clustering finds communities in social networks, biological systems, and knowledge graphs. In computer vision, PCA and related methods compress image data while preserving essential features. In AI research, spectral methods are used in graph neural networks and manifold learning, where hidden geometry is key. In short, spectral theory lets us find structure in chaos, simplifying complex systems into manageable insights. So, spectral theory teaches us that hidden within every dataset, graph, or system is a spectrum, a set of signals waiting to be uncovered. Whether in networks, AI, or physics, it's the mathematics of seeing the unseen. In our next episode, we'll turn to Bayesian mathematics, exploring probabilistic programming and uncertainty quantification. It's how AI learns to reason under uncertainty, make predictions, and update beliefs as new information arrives. Don't forget to follow us by clicking the link below and check out the full playlist in the description. Each episode brings us closer to mastering the mathematics that drives intelligence and technology.